Hello, welcome back, Math Scholars. Professor McMath here. We're going to talk about a new type of number, E. Again, mathematics, we like making letters numbers, and E is no exception. It's a special type of number which we'll discuss, and then its relation to the idea of what a natural logarithm is. So first off, E. So pi and radical 2 are very common irrational numbers. E is also another irrational number. Its value, again, never ending and never repeating, starts with 2.71828 and then kind of goes on forever. The exact value for E can be found using the idea of limits, which requires at least calculus or possibly even pre-calc, depending upon the level of the class. So in either case, in this context, we're not going to discuss how to actually find E, we're just going to talk about how to use it. Now on your calculator, your E value, the button you'll use, will be on the bottom left side, typically with the the button that says ln, which is what stands for the natural log. And the natural log is just simply a log which is base E. So instead of writing out log base E of x, we just write ln of x. That's our natural log. Very similar to how our common log, the log base 10, we don't write as log base 10, we just wrote as log. So whenever you're dealing with this E in its logarithm, you need to make sure you write it as ln. Now, because natural logs are just simply another type of logarithm with just a different base, all the different rules for rewriting logarithms to exponentials and vice versa will still apply. If I want to rewrite this exponential equation, e to the x equals 8 in logarithmic form, well, we always write it as log of the base, and we switch the two values, the x and the 8, so then become log base e of 8 equals x. Since it's log base e, we would just write that as ln 8. So in the future, I'm not going to be writing log base e again. It's just something that you just need to naturally know that when you rewrite exponential into logarithm, it's ln, not log base e. Alright, so that's all we do. It's in the same rules that apply. It's the base stays the same and the two other values switch. Again, if it was with the base originally, it cannot be with the base in the new form. And the same as when it's the opposite. If it's a natural log and I want to rewrite it as an exponential, we need to recognize the base is still e, and again, the other two values have to switch. X was originally with the logarithm, so it cannot be with e then. So it's e to the 10th equals x. So again, in those previous videos, the different times we talked about how to rewrite log equations or exponential equations, still applying here just with base e. Condensing and expanding is still the same rules with the natural log as it is with regular logarithms. The number in front becomes the exponent, so this becomes ln of 10 cubed. If we're subtracting, that's still the same thing as now dividing the insides. So 10 cubed over 8, which since these are numbers, we can evaluate 10 cubed as 1,000, and 1,000 divided by 8 is 125. So that's the condensed version of this natural log. Again, if they were all variables, this would still be true. If it was like 3 ln x minus ln y, the 3 still goes to the exponents. Because we're subtracting common base logarithms, we still then divide x cubed over y. Okay, so whether it's numbers or just variables, we still apply the same rules. So if we have ln 40 plus 2 ln 1/2 plus ln x, again, the number in front becomes the exponent. So we would have ln 40 plus ln 1/2 to the second power plus ln x. And since we're adding all these, that condenses as a product, so it'll be 40 times, well, since it's the number we should evaluate this, 1/2 squared means 1/2 times 1/2, which is 1/4, and then times x, which works out to be ln of 10x. So there's our condensed version right there. Again, fairly straightforward, still using the same rules, so nothing tricky is happening with this. One other practical application of E is the idea of continuously compounding interest. So we remember we had this compound interest formula, A equals P times 1 plus R over N to the NT power. Well, continuously compounding means we're compounding infinitely. It's pretty much every single second, every single half second, it's constantly being compounded. So N is going to infinity. Now, being compounded constantly does not necessarily mean you're going to have a much larger net worth because of that. Again, if you look at this, if n goes to infinity, we're doing r divided by an incredibly large number, this pretty much goes to 0. But then the exponent also kind of goes to infinity as well, so what's really happening? That's where the idea of limits and calculus comes into play, to take this equation as n goes to infinity and make it into this equation. Again, not something we're discussing in this particular class, something you'll see pre-calc possibly, definitely in calculus. So the variables are all still the same. A is still the account after the t years, so it's still your final amount. P is still your starting amount, the principal investment, the initial investment. R is still an annual interest rate raised as decimal. And then T still has to be time. Again, has to be the same rate as R, so if R is like 4% per year, then T has to be in years. So if it was like T is like 3 months, then we need to know T is 1/4 then. So when we're plugging in and using this, it's a fairly straightforward prospect. All we have to do is plug in the information. So Castell invests $3,029 in a savings account, fixed annual interest rate of 6% compounded continuously. What will be the account balance after 11 years? So we want to know the final balance. So we want to know our A value. Our initial investment is at $3,029. That's E. Our interest rate is 0.06, and our years is 11. So for this case right here, when we're trying to find a final amount, we just plug directly in and we just type it out the way it seems. 3,029 times E, that's where you're going to have to probably use your second function with the ln bun on the left-hand side. It's going to give you an exponent. Please make sure the 0.06 times 11 are both in the exponent. And you should be getting, now this is money, so we'll round to the hundreds place, $5,860.49. There we go. Want a final amount? It's very straightforward, very easy. Now for this one, we want to know how long it's going to take. It says Leah invests $3,642 in a savings account, annual fixed rate of 8% compound continuously. How long will it take to reach this account balance? Now we want to find a time. So when we plug into this, we have our final amount, the $5,433.23 equals our initial investment, $3,642, times e to the 0.08 t, which I'll use an x because I personally cannot stand writing t's in math. They look like plus signs, and if you try and write it cursive, it looks stupid, so I'm just going to stick with an x. Now, the variable in this case is the exponent. So this one requires to use our rules for rewriting exponential equations to solve for it. So what we're going to do first is we need to isolate the exponential parts. We divide by the 3,642. Now, I don't want you using your calculator just yet. Leave this fraction alone. Most likely this fraction is not nice, and we want to make sure we're using exact numbers to get our answer. So it'll be 5,433.23 over 3,642 equals e to the 0.08x. Here's where we now rewrite this as a logarithm. So we keep it, so it's ln because the base was e, and then we switch the two pieces. 0.08x was with the, so it cannot be within the logarithm now. So now it's at fraction 5,433.23 over 3,642 equals the 0.08x. Again, rewriting as the exponential allows us to get the exponent down into a linear fashion, no longer in exponent position. Now we can actually solve. All it's left to do is divide by 0.08. So now, at this point now that we have everything done, we type it into our calculator the way it appears. Make sure you close off your parentheses for that fraction, otherwise you'll accidentally divide 0.08 inside the logarithm instead of on the outside. So it's natural log, should just be the button on the left-hand side. 5,433.23 divided by 3,642. Be sure to close off that parentheses and then divide by 0.08. You're getting 5.00000, a whole bunch of zeros, which is just 5 years then. If it was actual numbers we can use, like it was like 5.2, then we would say 5.2. Don't worry about trying to make it into like months and days and all that other nonsense. Just round it appropriately. There's so many zeros at the end. Even if we go to the 10,000s place, it's still 0.40, so no need to go further. Alright, so that's how we use our rules for rewriting exponentials now to solve for the missing time. When we first talked about compound interest, we didn't do that because we had not yet, at least in my class, discussed the idea of how to rewrite the exponential yet. Now we do, so now we can solve for time, which means we can also solve for the interest rate. So Nicole invests $8,632 into a savings account, fixed annual interest rate compounded continuously. After 10 years, the balance reaches $21,231.29. What is the interest rate of the account? So we're still going to plug in the same way. 21,231.29, 8,632, e to the 10 r. We still divide to get rid of the number in front of the exponential. We still then rewrite the exponential as a logarithm to allow us to solve for the exponent, so it's ln of the fraction. And again, we're still not using our calculator just yet to type this out. We want to wait to the end. Then we still divide by 10 to get to our answer. Now remember, R needs to be a percentage. So when you're done, you get your answer, you're going to have to multiply by 100 again to convert from the decimal to the percent. So we have our natural log of our fraction. When we divide that by 10, it gives us 0.08 and then a whole bunch of 9s. Remember to multiply by 100 to get to percent. So if it's 8.9 and a whole bunch of 9s, this is really going to be rounding up to 9% then. Oops. I believe, as usual, the pen decides to just stop working halfway through. I have no idea why it does that. It drives me absolutely nuts. So we'll fix that in just a second. But anyway, 9%. Alright, give me a moment, I'll fix that. Okay, so there we go. Again, with all these problems, you really want to avoid using the calculator until you have the variable solved for itself, so just rewrite the equation and then type it in one step. This reduces the possibility of rounding errors and other mistakes that might occur from this. Well, we talked about how to find the final amounts, the interest rate, and the time, so let's talk about how to find the initial investments. So, we investing a sum of money, interest rate 9%, 10 years, balance reaching 17,000, blah, blah, blah. Find the initial investment. So our 17,918.21 is our final amount. We don't know the initial investment. Sorry, that's P not A. It's e to the 10 times 0.09. Well, this e raised to the power of 10 times 0.09 is some number. If I want to solve for p, I always divide by the number it's multiplying with. So I would just divide by e to the 10 times 0.09. And that's all we're going to type into our calculator. There's no need to go through any other interesting stuff. There's no need to rewrite an exponential or that kind of stuff. We just divide by the exponential part. So 17,918.21 divided by e to the 10 times 0.09. And we're going to get 7,285.00, so $7,285. There we go. There's our initial investment. Okay, so that's the idea of using our, the idea of what the E is and what the natural log does, and then an actual practical application from that. Alright, so again, that's all I have for you today with this particular topic. I'll see you next time we start talking about how to solve log equations then. We've talked about exponential equations, we haven't gotten to log equations yet, so that's coming up. Alright, so McMath is out. I'll see you next time.